Good evening. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course, course ID NOC 26-ME20. And it's a 12-week course being conducted by Department of Mechanical Engineering, IIT Guwahati, under NPTEL program. And we are into ninth week of this course. Instructor for the course is Professor Niranjan Sahu from again Department of Mechanical Engineering, IIT Guwahati, and I am a research scholar here. So the theme of this week's content is supersonic nozzles and diffusers, right? So three lectures are there in this week's content. Lecture number 20 to lecture number 22. So here we are discussing nozzles and diffusers. So we'll wait for a few minutes to see if somebody joins. After that, we can start today's session. Thank you. Okay, so we can start with today's session. So, supersonic nozzles and diffusers. Three lectures are there. We shall start with lecture number 20. We shall see its topics and few questions related to this lecture. Then we'll move on to lecture 21 and few questions related to that. In lecture number 21, we have few numericals also based on some data. After that, last lecture is on diffusers. Okay. So this is there. So let's start. So topics in lecture number 20 that have been covered. One is your shock waves and expansion waves. So this we have discussed in previous lectures, right? So we saw how to model compression waves, how to model expansion waves. Then we saw properties related to normal shock waves. Then we studied oblique shock waves. Then we moved on to expansion waves. Okay. So it's an overview of that. From there, we move on to isentropic flow through variable area duct. So if you remember in your week 3, so there we have discussed using area rule that with area change, how the Mach changes for a flow. Okay. Be the flow, duct uh, converging, be it diverging. So in these cases, how your flow behaves and how this is related to your Mach number. So there we also saw area Mach number rule. Then is your isentropic supersonic nozzle flow. Okay, if we see, so if you see this, so this is from week number 3. Okay, lecture number 8. So this we have discussed here. This is isentropic supersonic flow. So it is like this. Okay. This is your basically nozzle. Okay, this is entry. This is exit. So this is a convergent divergent nozzle. So talking about Mach number. So from stagnation condition, sorry. So from your stagnation condition here, let's see. We have some reservoir here, okay? So from there, we are getting some stagnation condition, some initial pressure, temperature, okay? So from there, this uh, reservoir is connected to this nozzle. So this is accelerating. So at the throat, it will be having maximum Mach, okay? So at your throat, it will be having Mach 1, and then further it will expand and its Mach will increase. When you have supersonic flow, isentropic supersonic flow in your nozzle. Okay. And how the pressure behaves? Now, because velocity of the flow is increasing, obviously its pressure is going to go down. Okay. So its static pressure is going to go down and it looks something like this. So it looks something like this. So this is your x direction. Now what is 0.528? So we have seen previously, right? So at your throat for nozzles. So this ratio we have come across in one of the previous lectures. So at throat, when your throat is choked, the static pressure with respect to your stagnation pressure, this ratio is going to be 0.528. Now this is for your static temperature. And at throat, the static temperature is 0.833 of the stagnation temperature. So this is about your isentropic supersonic flow. And for your density, the ratio is, if I remember it correctly, it's 0.63 something. Okay. Then next, if you see, is your isentropic subsonic flow. Now in isentropic subsonic flow, what happens is your subsonic nozzle flow. So what happens is your flow is going to remain subsonic in your whole of your nozzle. Okay. So I'll again draw this ED nozzle first. So here the pressure ratios, okay. What is your pressure at the entry and what is your pressure at the exit? So these ratios play a very important role. Okay. So again, this is your throat. This is your MAC. This is your X direction. Okay. So it's like this. In between, maybe I'll draw this. This is one, this is two, this is three. Okay. So this is isentropic subsonic nozzle flow. So what happens is, so there is pressure at your entry and there is pressure at your exit, right? Now your pressure at your entry has to be high with respect to your pressure at the exit, only then you're having to have flow. Now, if your pressure at the exit is not sufficiently low, the flow at your throat is not going to get choked. Okay. So, so when your flow is choked, right? So you'll have some equation, right, of your pressure at entry and pressure at your exit. So this ratio you'll have, right? Now, if this ratio is not favoring the choking, right? So this the flow at the throat is going to be subsonic. So if you see one and two, so they depict that only, right? So this is your three. So this is your three, this is your two, this is your one, right? So if you see your third case, so your MAC is higher at the throat, okay, with respect to 1 and 2. And the pressure is the lowest for the third. The MAC is the highest and the pressure is the lowest. So this is when your flow is choked. Okay, if your exit pressure is high, like in the case of first and second, then your flow is going to remain subsonic throughout, even at your throat. So this basically is your isentropic subsonic nozzle flow. Then you have one diagram that is of your mass flow rate and your exit pressure. Okay, and it looks something like this. So this is your choked flow. Now you see if you, so this here is exit pressure. Now you see uh, at your x-axis. So if this pressure keeps on reducing, right, your mass flow rate starts moving towards your choked flow. And one point comes, uh, and one point comes where if you go below this pressure, so there is not going to be any difference in the mass flow rate. So your flow is going to remain choked, and further you cannot increase the mass flow rate in this nozzle. Okay. So this is your topics on lecture number 20. Okay. Then we shall see questions. And then numericals also have been discussed. So for numericals, you can go through the uh, lecture videos. So I'll just give the link in the description of this lecture and all the lectures I'm going to give. So I've been doing this for all the tutorials. Okay. So first question says that it's a very simple questions. Such type of questions you have seen in your assignments. So first question says that irrespective of nozzle diffuser action in the passage, the flow is subsonic at dash of the duct. So whether this is entrance, throat, exit, or no option is correct. So the answer to this question is very simple. Okay, B, at the throat, be it diffuser action, be it nozzle action. Okay. Diffuser action means you are slowing down the flow or you're compressing the flow. Nozzle action is you're expanding the flow and you're increasing the velocity of the flow. So this is question number 1. The next question is, by mistake, two options here are same. Anyways, so please read this question and try to answer this. Question number 2. Please read this question and try to think and answer for this question. So the question here says that the Mach number at the exit of nozzle is fixed by the area ratio between dash and dash. So this is there. Now its answer we have from where? So we have seen, so if you revise your lecture number 9, okay, from your lecture number 9, you have this area Mach number relation, which will tell you that area ratios are related this way. So they are related this way. Now, one area is this one is for your throat. Okay. And this area is for the cross section in the variable area duct where you want to get your Mach number. Okay. So this area then becomes area at the exit. Okay. Now if you see the Mach number at the exit, and this is the Mach number at the exit. Okay, because at the throat for your supersonic nozzle flow, at the throat you're going to have Mach 1. Okay, and this Mach is for your cross section where you want to get the Mach. So Mach number then ratios this become throat and exit. Okay, D option it comes out. I hope this is clear. Question number 2. In question number 3, please use this question and try to give an answer in the comment box whether the statement is true or false. So here the question says that below the exit pressure corresponding to the choked mass flow rate, the flow properties at the throat and entire subsonic section change with change in the exit pressure. Okay. So I hope the question is understood. Okay. So this basically says that first it talks about exit pressure for your choked mass flow rate. Okay, so let's see this using a figure. Okay, so this is your choked. The third position is your choked case. Okay, now this, and there is some exit pressure corresponding to this. Let's say this is PE3. Now before this was not choked. Okay, PE1, PE2, this was not choked. At PE3, the flow has got choked. Now below the exit pressure corresponding, now what we are want to do, we want the exit pressure to be lower than PE3. Okay, for your question number 3, we want our pressure to be lower than PE3 exit pressure. Now it says that the flow properties at the throat and entire subsonic section change with change in the exit pressure. Now it says that now that we have changed this exit pressure to a lower value. Okay. So now that we have changed this to a lower value, so will it affect this region? Okay, because this region was subsonic region and here it becomes sonic. Okay, so is this region going to get affected? So the answer to this is no. Okay, so this region is not going to get affected. There will be no change in this region if you further decrease the exit pressure, or further if your exit pressure decreases. So because the question says that it changes, so this becomes a false statement. Okay, I hope this is clear. Then question number 4. So please read this question and try to give an answer. So question number 4 says that a minimum area at the throat in a nozzle is sufficient condition for the flow to be choked. So in a nozzle, if you have some nozzle with some minimum area, so is that sufficient condition for the flow to be choked? So this is not true. Why so? So we have seen here, okay? So we need to have some pressure ratio related to your entry and exit. So with respect to your what pressure you have at the entry, you need to maintain some exit pressure, some minimum exit pressure you require. Okay. Above that pressure, if you have some pressure, so your flow is not going to be choked, even if you have some uh, minimum area in your CD nozzle. Okay. So just by having some throat in a nozzle, you're not going to get your nozzle choked. So you need to have some minimum pressure at the exit. Okay. So in that case, this is a false statement. Then we have lecture number 21. So these are topics related to lecture number 21. So first, the shocks and expansion waves. So again, an overview of these two topics has been given, first of all. Then you again move on to isentropic flow through nozzle. Okay. Then adiabatic nozzle flow you see. Then normal shock formation in your nozzle. So this we shall see. Then overexpanded nozzle has been discussed. Then underexpanded nozzle has been discussed. Okay. Then this topic is there. Okay. So these are the topics in your lecture number 21. Okay. So isentropic flow through nozzle we have seen in previous lecture. Okay. Then in adiabatic nozzle flow, you are going to have normal shocks. Okay. In your divergent section of your CD nozzle. Then at the exit, you are going to have oblique shocks and expansion waves based on the equation that you have between your exit pressure and your back pressure. Okay. So there are two things. One is your exit pressure and one is your back pressure. So exit pressure basically is pressure that is because of the flow. Okay. When we say that uh, at this cross section, your flow is having this static pressure. Okay. So this should be clear between these two. Lecture number 21. This is there. So now this is your exit. Okay. So what happens is your flow is moving through this nozzle. Okay. So let's say at some point this flow reaches. Now at this point your flow is going to have some static pressure, right? Same way when the flow again advances and reaches here, it is going to have some static pressure. Okay. So this static pressure basically has been called as the exit pressure, PE, with the subscript E. P with the subscript E. Small p with the subscript E has been called the static pressure. Now there is one more term that is PB, that is back pressure. So that basically is the pressure that is in the atmosphere, right? So one pressure is here at the reservoir, then this back pressure is in the atmosphere. Now this reservoir and back pressure are going to give this uh, flow in the nozzle. Okay. So in your isentropic flow, your pressure behaves like this. Okay. In your subsonic flow, your pressure behaves like this. Okay, 1 and 2. Now what happens is that so this is your y-axis static pressure. This is your x direction of your. So you have shock at this point. So now what happens is, so we have seen the isentropic supersonic solution, right? So this is this. Okay. Now we know about subsonic isentropic solution also. So now what happens is, and there are back pressures related to these two cases, right? So first is supersonic isentropic solution, then is subsonic isentropic solution. For that, there are lots of back pressures that can give this subsonic isentropic solution. Okay. Then for some particular this back pressure related to your reservoir pressure, you're going to have a sonic condition, right? Now, in between these two, we have some back pressure, right? Now, what happens is that now your uh, flow first starts from entry, okay? It accelerates, the throat gets choked. At the throat, you have sonic flow. Now, what happens is the back pressure is such that your flow can further expand. Okay, so your flow can further expand from your throat. Now, but in between, while it is in this divergent section, okay, when it is in divergent this section, when it is in divergent section, so in between, because this is continuously your flow is expanding, right? And your pressure is going down, right? Now, you're at some point, your pressure is such that this has overexpanded, right? To its fullest. Now, further, it cannot expand. So in that case, what happens is that you get a normal shock here. Okay. Now, so this is overexpanded case. Okay. This is overexpanded case. Now there is another case. So if your back pressure goes below this point, so let's say this is 1 point, this is 2 point. So now if your back pressure goes below this point number 2, which is ideal case, which is isentropic flow case, right? So your isentropic flow case is your design case. Now, if it is going to go below this, so what will happen? So your exit pressure. So here what happens is, so in overexpanded case, your P exit is going to be less than PB. Okay. And in that case, we see a normal shock in inside the uh, divergent section. Okay. Now, if you further reduce the back pressure below 0.2, so what will happen to your exit pressure? So your exit pressure is such that it is still greater than your back pressure. So which essentially means that your the pressure of your flow, static pressure of your flow is higher than your back pressure, which means there is still some scope of expansion in the flow. That is why we are saying that it is under expanded. Okay. It hasn't expanded fully. So this is your under expanded case. So this is there. Okay. And now in your under expanded case, to balance the pressures, we get expansion waves. And here at the exit, we get oblique shocks. So this is the difference between your overexpanded case and underexpanded case. I hope this is clear. So this was there. Okay. Right then. Then we can move on to questions. I hope this is clear. Okay. So first is your subsonic isentropic solution. Okay. Then is your supersonic isentropic solution. And in between your subsonic and supersonic, you have your this overexpanded case where you get a shock in the divergent section. And then there is your underexpanded case, where your P exit is greater than, still greater than your back pressure, right? So this is there. And in your overexpanded case, you're going to get oblique shocks. And in your underexpanded case, you're going to get expansion waves. Then we have questions for this lecture. The first question is there. Please read this question and try to answer this. So this question is that in the adiabatic nozzle, there can be formation of oblique shocks and expansion waves in the divergent section. So whether this is true or false. So in the divergent section, you get a normal shock. Okay. So your oblique shock or expansion waves are at the exit of your nozzle. Also, when there are reflections or interaction of your shock wave or your expansion wave with their free boundary. So we have seen in previous week's content that for your oblique shocks, you get expansion waves, and for expansion waves, you get oblique shocks. Okay. So that is there. So this is question number 5. This is false. So this is question number 6. Please read this question. And try to answer this. So this question is on slip line. What is a slip line? So for same family of oblique shocks, we see here the concept of slip line has been introduced. Okay. Then here you see for opposite family, left running and right running oblique shocks. For that you have this slip line concept. And why this slip line concept was introduced? Because there were entropy differences. Okay. The velocity direction was same across this slip line. And the static pressures were also same. But the only difference was of entropies. Okay. So same way here across the slip line pressure must be same, but velocities can be in different directions. So that is not true. That is a false statement. Okay. So this is question number 6. The next question we shall see after taking a short break. Okay. So let's take a short break after that for 5-10 minutes. After that, we can continue with our session. Thank you. Okay, so we can continue with the remaining session. So question number 7. So please read the question first, then try to see whether this is a true statement or a false statement. So this says that let there be a normal shock formation in the divergent section of the nozzle for an exit pressure. If the exit pressure is reduced further, the normal shock will move in downstream direction. So whether this is true or false. So here, if your exit pressure, so let's say you have exit pressure at 1, okay. Now if you move your exit pressure here to 1 dash location, so your this shock is going to again go downward in your divergent section, okay. So in that case, this is a true statement. Right? Then next question. In your under expanded nozzle, there is formation of oblique shock at the exit. So in your under expanded case, what happens is your P exit is still greater than your back pressure. Okay. So your exit pressure is still greater than your back pressure, and then there is scope of sorry. So there is scope of expansion. Again, there is scope of expansion. So now if you're going to have an oblique shock, so your pressure is going to increase. Okay, so that is not going to go well with your back pressure. So if you want to reduce the pressure, you're going to need an expansion wave, right? So there is formation of expansion wave at the exit. So this is a false statement. Question number 8. Then in the next set of questions, for next set of questions, we have data. It says that reservoir pressure is this. Okay. So reservoir pressure, question number 9 to 12. So P naught is given here as 12 atmosphere. The reservoir temperature 520 Kelvin. Exit pressure 5824. Atmosphere. Throat area is 0.53, 0.35, 0.35 meters square throat area. Then Mach at exit is 5.3. Just give me a second. So temperature, you have this reservoir temperature at 520 Kelvin. Okay. Exit Mach number at the exit you have given. Exit to throat area ratio is given as 22. So AE by A star is given as 22. So this is there. Then coming on to questions. Calculate the exit area. So exit area we have to calculate. This is question number 9 solution. So AE by A star is 22. A star is 0.35 meters square, implies A exit is 22 into 0.35, that is equal to 7.7 meters square. So this is there. So question number 9, this was. Then question number 10, solution. Calculate the exit temperature in Kelvin. So exit temperature we have to calculate. So we'll use the isentropic ratios. Okay, the isentropic relations. So your T naught by T static, okay, at some cross section in the nozzle. So this is 1 plus gamma minus 1 by 2 m exit square. So this is there. Okay. Or your T exit by this 1 plus gamma minus 1 by 2. We'll write it this way. Then this becomes 1 plus gamma 1.4 will take. So this will become 0.4 by 2. At exit, your Mach is 5.3. So this is there. Now, if you calculate this, this will come out to be 0.1511. Please cross check the calculations. So I'm getting this 78.757 Kelvin at exit of this nozzle. Now it says that calculate the exit pressure. So now exit pressure we need to calculate. So this is basically this is this P naught by P static, P stagnation by P static. This is 1 plus gamma minus 1 by 2 me square raised to power gamma by gamma minus 1. Implies P exit by P naught is 1 plus gamma minus 1 by 2 me square minus gamma by gamma minus 1. So this is there. Then if you now place the values here, okay. So let's calculate this. Yes, so I'm getting 1.34 into 10 raised to power minus 3. This ratio I'm getting this. So implies P exit is equal to, based on your P naught, your P naught is 12 atmosphere. So based on your P naught, 1.34 into 10 raised to power minus 3 into P naught is 12. So this is coming out to be 0.0160 atmosphere. So this has not been converted into Pascal. So this is atmosphere. So this was an atmosphere. This was an atmosphere. So this is 0.0160. Then it says that calculate the mass flow rate in kg per second. Question number 12, this is so this is rho AV. Yes, mass flow rate is rho AV, area and velocity. Now we have Mach at the exit. Or VE, velocity at the exit. So now we have Mach at the exit, so we can get the speed of sound. Okay, and from there, because Mach is UE by or VE by AE. So AE we can find out. This we have, this we can find out and we can get VE. Okay. Area at the exit we have. Density also we need to calculate. So AE is rho RTE root. So this is 1.4 into 287 into 78.57. So we have calculated this. So taking root, so this is here, this is. This comes out to be 177.67 meter per second. So this comes out to be this. Then your VE becomes 5.3 into 1.77.67. So this comes out to be 941.651 meter per second. So this is there. Now to find out the rho E, we can use pressure is equal to rho RT. Implies P exit is 0.016 atmosphere. Now we will convert into pascals. 287 into 78.57. Implies your rho E becomes 287 into 78.57. So your rho E becomes this. So hence your mass flow rate is rho E AEVE. So this is 0.0718 into 7.7. Okay. 7.7 from question number 9. And then VE, that is 941.6. So this comes out to be 520.57 meters per second. So this is there. Question number 12. So this is it about lecture number 21, then lecture number 22. In concepts of nozzles and diffusers. So this has been discussed. Then supersonic wind tunnels, supersonic flow in nozzles, supersonic diffusers, diffuser throat, diffuser efficiency, summary, numerical problems. So here what do we have? The supersonic wind tunnel, if you see, lecture number 22. So in your supersonic wind tunnel, you're going to have one reservoir. Then you're going to have a nozzle, CD nozzle. Then a test section you're going to have. This is throat. Now from here, you are going to have a diffuser. Diffuser, nozzle, test section, reservoir. So this is there. So you'll have pressure at reservoir. Okay. Then you'll use a nozzle to accelerate the flow. Then at test section, you're going to have your required flow. Then we need to decelerate the flow. For decelerating the flow, we use a diffuser. All right. Then to have minimal losses, minimum pressure loss we want to have. So what we use oblique shocks. Okay. So as you can see, this section, so this section, A section, so B section, C section. So B section, if you see, so the flow will turn towards itself. It will create oblique shocks. Okay. So one main benefit of oblique shocks is that it compresses the flow. It decelerates the flow and compresses the flow with pressure loss. The pressure loss, the total pressure loss. Okay. The total pressure loss, if you compare it with the normal shock, it is less here in oblique shocks, right? So a series of oblique shocks we use to decelerate the flow. Then eventually at the exit of this section, you are going to have a very weak normal shock so that your pressure losses are not high. Okay. So this is there in your supersonic wind tunnel. Then you have this as throat 1 and this as throat 2. Okay. Two throats are there. One throat is related to your nozzle, one throat is related to your diffuser, right? Now related to your throats. So your throat 2 area of throat 2 is greater than area of throat 1. First is this. Now the behavior of your throat and the efficiency of your diffuser. Okay, how efficient your diffuser is based on the pressure data. So we have a graph for this. It is this way. Okay. So your maximum efficiency will be at this point. If further, if the area of this second throat of the diffuser is decreased, so this will lead to further decrease in your efficiency. Okay, as you can see, so if I say this is A, B, C, from B to A, if you see, if your area is decreasing, with that your efficiency is also decreasing. Same is the case for your BC curve, right? So if your here also your efficiency will decrease. So on both sides of your point B, your efficiency is going to decrease, whichever way you go, right? So this is your diffuser efficiency. Then we have questions. So question number 13 is there, which is that a supersonic wind tunnel is designed to compress stagnant gas to supersonic speeds. So this should be expand and not compress, right? So this becomes a false statement, right? Then question number 14, how many throats are, so there are two throats, right? B option is correct option. I hope this is clear. The performance of a supersonic wind tunnel depends on the performance of its dash. So the efficiency of a wind tunnel depends on its diffuser, supersonic diffuser. Okay, so B option is the correct one. I hope there's no doubt in it. If so, you can write in the comment box. Question number 16, a supersonic wind tunnel, the first throat is larger than the second throat. So that is not true. Your second throat is larger. Okay, so this is there. Then last question. When the convergent part of the diffuser changes the flow direction at wall, it encounters compression corners for which the oblique shocks are formed inside the duct and the total pressure drops. Okay, so this talks about this section, section number B. Okay, in your supersonic wind tunnel. So this is true statement. Okay, your pressure will also drop and oblique shocks will be formed because your flow is moving towards itself. So this is it about today's session on your supersonic nozzles and diffusers. Okay, so here we saw, so one important topic was your adiabatic nozzle flow. Okay, that you need to keep in mind. So we started with the isentropic nozzle flow, supersonic nozzle flow, then subsonic nozzle flow. Then we saw adiabatic in lecture number 21. We saw adiabatic nozzle flow. Okay. What is a choked flow, that we also saw, right? Now the normal shock, why normal shock forms in a divergent section in a adiabatic nozzle flow. Then there are overexpanded and underexpanded cases in a nozzle. So what are these? What is the design condition? Yes. Then we saw your supersonic wind tunnel and then supersonic diffuser in it. So this was it about week number 9. So next session again will be on coming Tuesday with same timing 6 to 8 p.m. Till then, goodbye. Thank you. And thanks for watching this session.